Hi team, it's Mr. Zimmerman, and today we're going to look at equivalent expressions and basically talk about how things that look completely different might actually be the same thing. So let's go ahead and dive on in. So up at the top, you might notice I'm reviewing a bit of vocabulary, an expression, and an equation. And the difference between these two math sentences is that one of them has an equal sign. You notice equation, EQUA. That's how you spell equal. That's how I remember, oh, an equation has an equal sign. Now, this has already came up because when we were factoring, for example, if I had x squared plus 3x plus 1 equals 0, here is a situation where I can use the quadratic formula, and this is because it's an equation. However, if I had just x squared plus 3x plus 1, this is an expression. I would not be able to use my quadratic formula to determine the solutions. I could factor it, but that's another discussion for another day. So what we're talking about here is, can things that look different be the same? And the answer is yes. Most of you have an autopilot where you want to automatically combine these and know that repeated addition, this is going to be 4x, and 2x's make 4x. Are these expressions equivalent? Yes. Yes, they are. They look completely different. I want to reference regular fractions. 1/2 is the same as 50 over 100. Both of these look different, but they have an identical value. Now, this is where we're going to go ahead and review. This is going to look like linear, and we're going to look at it, but I want to take the opportunity to go ahead and just graph. With technology, I can go ahead and simply plug in 4x. I'm going to use Desmos, and I'm going to show you how easy it is going to be. So Desmos, I go over here, and I'm going to just type in 4x. Voila. Here's my expression being graphed as if it was an equation, and I see it's definitely a line. Now there's a bunch more to this line. We notice that it has a y-intercept of 0, 0. I also can tell immediately that the slope is going to be increasing because it's going from left to right and increasing. The other part I want to highlight is I can also make these conclusions just looking at the linear representation. By looking at this and comparing it to the typical form, mx plus b, I can conclude that the slope for m is going to tell me if it's a positive m, that means it's going to be increasing. If it's a negative slope, it's going to be decreasing. And then this b is going to tell me what is the y-intercept. Now you might be asking yourself, hey, I see a 4 is m, I see the x, where's the b? Well, the intercept's at 0 where we saw it. Also, it's adding nothing is the same as me representing it. That was a lot right now, but all I'm trying to show you is that you should be able to visualize what some of these will look with graphing. Yes, you can use technology, but you need to build the muscle memory to get a visual image in your head without using the technology. Number 2 is very similar. I distribute and I get 2x plus 8, and I know it is not the same. This plus 8 and this minus 8 is a game changer. So they're not the same, and I know without even graphing that both of these are linear. The reason I know is mx plus b. I have 2x plus 8 and 2x minus 8. If I were to go ahead and graph both of those, 2x plus 8, 2x minus 8, what difference visually does this change cause? And the reason I like Desmos is if I click on it, it instantly tells you what the intercept is. 0, 8, -8. Okay, that's what it does. So both of these are linear, and the reason being is that they resemble slope intercept form. So I want to